At the bottom of the Pacific Ocean, buried in a slab of rock that took millions of years to form, scientists found something that should not be there: atoms of a metal called iron-60. Now, iron-60 is radioactive. It decays. It disappears. Given a few million years, every last atom of it vanishes, which means any iron-60 that existed when the Earth formed died out billions of years ago. And yet, there it was, fresh, recent, sprinkled through the ocean crust like ash. There is only one place in the universe that makes iron-60 in these quantities: the heart of an exploding star. Which leads to a conclusion that sounds insane the first time you hear it. In the recent past, while our ancestors were walking the Earth, a star exploded close enough to us that its debris rained down onto our planet. And that explosion wasn't a one-off. It was part of a chain of stellar detonations that carved out a vast, glowing cavity in our corner of the galaxy, a cavity we are flying through right now. Tonight, we're investigating a cosmic crime scene, and the evidence is buried under your feet. Let's start with a question almost nobody thinks to ask. What is the sun flying through? We picture space as empty. It isn't. The space between stars is filled with a thin fog of gas and dust, the interstellar medium. It's the raw material of the galaxy. In most places, it just sits there, drifting at a fairly predictable density. But in the 1970s and 80s, astronomers studying our own neighborhood noticed something odd. Around the sun, in every direction they looked, the fog was missing. For hundreds of light years, space was up to 1,000 times emptier than it should be. And the edges of this empty region weren't calm either. They were hot, traced by X-rays, like the walls of a cave that had been scorched. They had discovered that our solar system sits inside an enormous cavity, roughly 1,000 light-years across, now called the local bubble. Think about what that means for a second. Every single star you can see with your naked eye on a dark night, most of them live inside or on the walls of this same bubble. Our entire visible sky is, in a sense, the inside of a cavern. So the obvious question: what makes 1,000 light-year hole in a galaxy? You can't blow a bubble that size with stellar winds. You can't do it with one explosion either. The math points to something far more violent. To carve the local bubble, you would need on the order of 15 supernovae, 15 massive stars detonating one after another over about 14 million years, each blast slamming into the fog and sweeping it outward like a snowplow made of shockwaves, a chain of stellar detonations in our galactic backyard. And in 2022, astronomers using data from the Gaia Space Telescope reconstructed the whole event and discovered something with an almost cinematic twist. Nearly all the young stars forming near us today sit on the surface of the bubble because the expanding shockwave swept up gas and triggered their birth. The explosions that emptied our neighborhood also seeded it with new stars. Death, manufacturing life. Keep that theme in mind. It's about to get personal. Here's the problem with astronomy. It's usually a spectator science. We watch, we can't touch. A supernova that happened millions of years ago should be the coldest of cold cases. The light is long gone. The debris has dispersed. What could possibly remain? The answer, it turns out, is shrapnel. When a massive star explodes, it doesn't just release light, it forges and ejects freshly made atoms, including that radioactive iron-60. And if the explosion happens close enough to a planet, some of those atoms will eventually drift down through its atmosphere, settle through its oceans, and get locked into the slowly growing rock of the seafloor. Deep sea crusts grow at an almost absurdly slow rate, a few millimeters per million years. which makes them something miraculous. A tape recorder, running continuously for tens of millions of years, recording everything that fell from the sky. In 1999 and then decisively in the 2000s and 2010s, physicists sliced these crusts open layer by layer and counted iron-60 atoms with some of the most sensitive instruments ever built. The signal was unmistakable, a clear spike of supernova debris arriving on Earth roughly 2 to 3 million years ago, and a second, older pulse around 7 million years ago. And then the confirmations started stacking up like a courtroom drama. Iron-60 in sediments from the Atlantic, the Pacific, and the Indian Ocean, a global signal. Iron-60 in fossilized bacteria, microscopic life that had actually absorbed supernova atoms into its body. Iron-60 in lunar soil brought back by the Apollo missions. The moon was dusted too. And, remarkably, iron-60 in Antarctic snow that fell within the last 20 years, plus a faint drizzle detected by spacecraft still arriving from interstellar space today. We haven't fully exited the debris field. Let that settle in. You can hold a piece of ocean rock in your hand, point to a layer, and say, "This is when the nearest star died." The explosion happened, most likely, around 300 light-years away or closer, probably from dying stars in a group called the Scorpius-Centaurus Association, the same stellar family whose blasts inflated the local bubble. Far enough that Earth survived, close enough that Earth was marked, but survived is doing a lot of work in that sentence, because 2 to 3 million years ago, something else happened on this planet. Something died. A lot of things died. Around the same time the iron-60 was falling, the boundary between the Pliocene and Pleistocene epochs, Earth's oceans suffered a mass die-off that most people have never heard of. It's called the Pliocene marine megafauna extinction, and it was brutal. By some estimates, over a third of the ocean's large animal species vanished. Ancient whales, giant sea turtles, sea cows, seabirds, and one victim you have heard of, Otodus Megalodon, the largest shark that ever lived. Now, I want to be careful here because this is where good science communication matters. The mainstream explanation for this extinction involves climate. Oceans cooled, sea levels swung, coastal habitats collapsed, food chains buckled. That's real, and it's probably the biggest factor. But in 2018, a team of researchers pointed out an eerie coincidence of timing and proposed a darker, contributing suspect. When a supernova bathes a planet from a few hundred light-years away, the flash itself isn't the main danger. The danger is the aftermath, a drawn-out flood of cosmic rays, high-energy particles that slam into the atmosphere and cascade downward as a spray of secondary radiation, including particles called muons. Muons are like heavy electrons, and they are very good at penetrating things. Water, flesh, hundreds of meters of ocean. Here's the cruel geometry of it. A small animal near the surface barely notices the change, but the bigger you are, the more muons pass through your body every second, and the higher your radiation dose climbs. The researchers estimated that for a large ocean animal, the mutation and cancer rates could have risen substantially for thousands of years. In other words, the die-off was strangely selective toward giants, and a supernova's radiation is also selective toward giants. Is it proven? No. Let me be absolutely clear. This is a hypothesis, debated, sitting alongside climate as a possible accomplice rather than the sole killer. But it is entirely possible that when the Megalodon disappeared from Earth's oceans, a dead star's fingerprints were on the scene. And there's one more twist in this timeline that scientists can't stop thinking about. 2 to 3 million years ago is also roughly when Africa's climate shifted drier, forests gave way to grasslands, and our own ancestors came down from the trees. Some researchers have even speculated that cosmic ray-induced lightning may have increased wildfires, accelerating the spread of savannas, the landscape that shaped early humans. Highly speculative? Absolutely. But sit with the possibility. The same cosmic explosion recorded in the ocean floor may be woven, even slightly, into the story of why you exist. So now the question you've been waiting to ask, could it happen again? And what if the next one is closer? Astronomers define a kill zone for supernovae, the distance inside which an explosion would deal serious damage to Earth's biosphere. Current estimates put it at roughly 25 to 30 light years. Inside that range, the radiation would shred the ozone layer, letting solar ultraviolet sterilize the surface layers of the ocean, the base of the food chain. Some scientists suspect an event like this contributed to a mass extinction 360 million years ago, at the end of the Devonian. So, is anything dangerous inside 30 light years? Here's the good news. No, not a single star close to us is massive enough to go supernova. Our immediate neighborhood is, frankly, boringly safe. The most famous candidate, Betelgeuse, the red shoulder of Orion that made headlines when it mysteriously dimmed, sits around 550 light-years away. When it goes off, and it will, it'll be a once-in-civilization spectacle, a new point of light rivaling the full moon, visible in daytime, for weeks. But it will not hurt us. We'll just get the greatest light show in human history. The more unsettling thought isn't the future, it's the past. Because the Iron 60 tells us that Earth has already been inside the blast radius of dying stars multiple times. Life on this planet has been repeatedly showered in the ashes of dead suns. Statistically, over Earth's 4.5 billion year lifetime, there have likely been dozens of supernovae close enough to leave a mark, and some researchers argue a few were close enough to reshape evolution itself. We think of extinction-level threats as asteroids, rocks, local hazards, but the fossil record may also be a record of astronomy, of every time the galaxy reached down and shuffled the deck. Step back and look at the whole picture, because it's stranger and more beautiful than any single piece. 15 stars died so that our corner of the galaxy could look the way it does. Their shock waves hollowed out a cavern of space 1,000 light-years wide, and along its walls, those same shock waves compressed the fog of the galaxy and ignited new stars. The bubble's edge is a stellar nursery built from stellar graves. Our sun, born elsewhere, long before, happened to drift into this cavern about 5 million years ago. We entered a crime scene already in progress. The debris of the final explosions fell onto our world, onto our moon, into the bodies of bacteria on the seafloor. And it is still falling, faintly, today. You have probably heard the phrase, "we are made of star stuff." It's true, but it's usually meant abstractly. Atoms forged billions of years ago, in stars long forgotten. This is not abstract. There are atoms in Earth's crust right now that were inside a living star while human ancestors were learning to walk. The sky didn't just make us in some distant past. The sky has been actively participating, killing giants, seeding stars, sprinkling its evidence across our ocean floors the entire time. We are not observers of the galaxy. We are residents, with everything that implies. The next time you're near the ocean, look down at the water and remember, somewhere far below, locked In slow-growing rock, there is ash from a star's funeral. And the next time you look up at Orion, find Betelgeuse, that red spark on the hunter's shoulder, and know that one day, without warning, it will become the brightest thing in the night sky. The universe isn't out there, it's in the ground, it's in the ocean, it's in you. If this one hooked you, you'll want to see what would happen if the sun simply vanished. That video's on screen now. Subscribe, because the universe's strangest cases keep coming. See you in the next one.